So now we're going to continue with reactions of alkenes, and specifically we're going to look at halogenation. So halogenation is the addition of a dihalide to an alkene. However, in this situation we're specifically looking at bromine or chlorine. This reaction doesn't really work with the others. If we try to run this reaction with fluorine, fluorine is generally too reactive. And we end up with complex mixtures of products, some of which are what we want and some of which are other things. Iodine is at the other end. It's very unreactive. Now it still works, but the reaction is generally slow and the products are unstable. One of the things we'll learn at the beginning of Organic 2 is that iodine is an excellent leaving group. And so even if you do get those iodines to add, it will usually revert back to starting materials. And that's something we haven't talked about yet with organic reactions. One of the things with organic reactions is that most organic reactions are completely reversible. If you recall learning about equilibrium in general chemistry, there certainly are organic reactions that essentially only go in one direction, but the overwhelming majority of them are completely reversible. And so, as we've seen before, we do often have to worry about equilibrium and how that affects whether a reaction can take place or not. And so we see here our first example. You can do halogenation with iodine, but the equilibrium strongly favors the starting materials. Now, before we get into the reaction itself, we want to define this term stereospecific, because this halogenation reaction will fit into that category. So stereospecific is a reaction that gives preference for a specific stereoisomer. And when we look at the reaction, we'll see what we mean by that. So the reaction in its most basic sense is that we take an alkene, we add bromine to it, usually in a solvent like dichloromethane. And the double bond goes away, and we get halogens on each carbon of what was the double bond. But as you can imagine, especially, and this is why I use a cyclic example, those two bromines could arrange in two different ways. They could be on the same side, cis to each other, or they could end up on opposite sides and be trans. So given that we just defined this term stereospecific, you might guess that there is a preference. And it turns out that the preference in this reaction is for the trans product. Now, why is that? Why is the trans product favored in this reaction? Well, in order to explain that, we have to look at the mechanism. So in this mechanism, the alkene attacks the temporary dipole of the bromine. After that happens, two other things happen. First is this bromine has to give up electrons, and so it completely gives them up by breaking the bond with the other bromine. But also, one of the lone pairs on that bromine comes back and attacks the other carbon of the alkene. So what we get is a three-membered ring containing bromine, where the bromine has a positive charge. Now that could happen on the top of the ring or on the bottom of the ring. Now how is it that this explains why we get the trans product in this reaction? Well, now the second bromine is going to attack. It's going to attack at one of the carbons of the three-membered ring and cause it to open up. This is a highly favorable step because it relieves a lot of ring strain by breaking open that three-membered ring. But if you look at what's going on, and this is one of those things that is very helpful to draw a model of, or to build a model, what you'll see is that three-membered ring is blocking part of the molecule. And so in order for anything to happen then, it's going to have to come in from the opposite side of where the first bromine is already. And as a result, the two bromines end up trans to each other. Now there will be a mixture of enantiomers, but regardless, both possible products are trans. Now, what does this mechanism look like for chlorine? Well, it's the same. And just to illustrate that, we can do that. But it is exactly the same mechanism when we use chlorine.